Okay. Uh, okay, right. Happy New Year, everybody. This is the first talk of 2025, and we are very happy to have Anamay Tengse here. Hopefully, everybody here knows who Anamay is. Even though we have been told that this borders on cliche, he was fortunate to be a grad student at FPPS a few years back, and he is now visiting faculty at NISER Bhubaneshwar. And he will tell us he'll tell us something about ROABP so that we can properly learn about them and then proper consent. Yeah.
Thank you. Thanks, all of you for joining. Yeah, so it's okay if so I'll be talking about what is called the order finding problem for ROABPs. I'll tell you what it is. So it sort of ties down to the missing piece in what is called proper learning or reconstruction of this model called ROABP. So I'll tell you more about it. Yeah, so let me get, okay, so this is a joint work with Vishwas, Bhargav, Pranjal, Dattu, and Sumanta Ghosh. Yeah, so let's start. So here is the problem that you might have heard from algebraic complexity or just about polynomials in general. It is called the PIT problem or the polynomial identity testing problem. So this particular variant is called the black box PIT problem because you don't get to see the circuit. So what is the problem? So you're given a black box, right? That computes a polynomial. Okay, and you're given some basic information about it. So you are told that it is on n variables, it is a degree D polynomial, and it has what is called an algebraic circuit of sizes. So not important what an algebraic circuit is, it just has some representation of sizes. It can be computed in sizes. That's the only thing you need to know. So what is the PIT problem with this black box? So what you want to do, or what an identity testing algorithm would want to do, is to interact with this black box by making queries. Right? So basically, it can query it on the point A1, which is A11 through A1n, which will go into X1 through Xn. And it can make some R many queries, and at the end, it has to basically tell whether the polynomial inside the black box is just the identically zero polynomial. Right? And identically zero here, you can think of it as it is zero on all inputs. No matter what is observed, it will just output zero. Right?
So how do you define the size?
So so size, just think of it as so the size is algebraic circuit size. Yeah. But as I said, like the definition of algebraic circuit is not important here. Basically, you want to say that so basically whenever the size S is far from trivial, far from the trivial upper bound, you want to say that this is an easy polynomial, so I should be able to figure out if it is zero or not. I mean, it is one of the easy polynomials, so I should be able to tell at least if it's a zero polynomial in some non-trivial number of queries. Okay, and so some of you might already know that. I mean, most of you already know. So there is a easy randomized algorithm for this problem, and it's a poly-time algorithm. Poly in the sense it's poly in all those parameters. Right. So you can do this easily. It's just the Schwarz-Zippel lemma, what is famously called the Schwarz-Zippel lemma. Okay, and this solves it for circuits as well, algebraic circuits in general. But what is open is, so basically what you want to do is, because we believe that randomized algorithms can be de-randomized, what you want to do is to de-randomize at least this particular thing. So can you get a deterministic algorithm, which is also polynomial time, but we are very far away from it. I mean, in fact, for circuits or for any general enough model of computation, the best thing that we know is basically D to the n queries, which is just, you look at the Schwarz-Zippel lemma and you say, I'm just going to go over the entire set instead of picking randomly or something. And as you can see that this S does not even appear in this. So we don't know how to use this advantage that it is a non-trivial polynomial. Right? So this is the PIT problem. So as I told you, this is hard for there are many other connections and reasons for why this is hard. So this is hard for circuits. So what people usually do is we look at simpler models and structured models, and ROABPs is going to be one such structured model. But so when we get PITs for structured models, what we go for is a more general problem called reconstruction. Like what one can go for is reconstruction. So what is reconstruction? Again, you have a black box. Okay. If we can have this, but critical. Yeah. So again, you have a black box, and what you want to do is to reconstruct this polynomial. This basically means you want to get hold of the polynomial completely. not just tell apart between it being 0 and non-zero. Just have the polynomial with you now. You want to recover the reconstruction. So how do you do it? Again, it's the same thing. Like because it's just a black box, what can you do? You can just ask it queries, right? So that's all the reconstruction algorithm is also allowed to do. Again, it gets some basic parameters, and it is told that for some class C, so now don't think of C as circuits in general, you can think of it as any simple model of computation. The model exactly I'll introduce soon, but yeah. So think of any simple thing, like maybe it has very few monomials or something, and like it has at most S monomials. Right? That is one case you can think of, and that is the size that we are going for. So reconstruction algorithm will, with this information, just these parameters, it will then come up with a way of querying this black box in many points, and will end up computing, like outputting a circuit that computes F. So now here again, circuit, like basically circuit in that model, whatever is that model. So it will give you a representation of F in that model. So whenever this C and this C is the same, like, so the black box came with a guarantee of size S being in some model. If the output is also of that model, if they are of the same type, then you say you have proper learned the polynomial, right? Otherwise, it's called improper learning. I'll just use reconstruction. Right? So yeah, so basically, if such an R sub C exists for the model C that you're thinking of, so it could be anything. It could be sum of monomials. It could be branching programs, anything.
So I couldn't follow the proper thing,
Uh-huh.
the proper learning.
So the proper thing just means that, so basically, okay, this may not be completely accurate, but think of it as you are just going to reproduce whatever is sitting inside this black box, you're supposed to output that.
So are there contexts known interesting contexts in which improper, in the sense that suppose you know that the circuit was depth-free, okay, but you output a polynomial with just outputting a circuit. Yeah, not necessarily of depth-free. Does that help? Is it known to
So the thing is, we don't have any. So we have proper learning algorithms for sparse polynomials and for ROABPs in some context. But at this moment, I don't think there is anything where we can do something. So yeah, so can do something in an improper way, but proper is not known.
I think we do. No, it's Cliven-Spilker.
Oh yeah.
Results no, Cliven-Spilker.
So, Cliven-Spilker, but they do reconstruct ROABPs, right? At the end.
Yeah, but
The input is there.
Oh, I see. Okay. Yeah.
So your guarantee you are given is that the black box holds a set multilinear depth-free circuit. But the reconstruction algorithm produces an ROAB.
Yeah.
But it is not known how to give a depth-free.
Yeah, in fact, I think it's hard. Like it's that because tensor rank, etc.
So yeah, but yeah, so technically it is a proper learning algorithm for ROABPs. But yeah, I mean,
yeah, that's true.
Yeah, because set multilinear depth-free circuits go inside
ROABPs. Has some recent work.
That's an interesting thing. So the algorithm can in fact learn ROABPs itself.
Yes.
That particular algorithm, but there are other instances where the only thing that we know is to do improper learning.
In the sense that, as he said, like it should not be that the algorithm is so powerful that it can learn the bigger class, even the hypothesis class of it is bigger.
So there are instances where we know improper learning algorithm, but it's not a proper learning for a larger class.
For algebraic
I
space.
see.
For algebraic.
I know such instances of Boolean function classes. You're right.
If we change sizes in the output of the reconstruction to size poly S and D.
Yeah. So
it's still proper.
yes, it will still be for. Yes.
You don't want the exact.
No. Yeah. So this is the proper learning setting. You have a black box. It has some representation of polynomial. You want to recover that like in the same format. That's the proper learning thing. That's called reconstruction. Right. So yeah. So this is the proper learning part. What is the ROABP part? So I'll now tell you about what are called read-once Oblivious ABPs. So first, let me tell you about what ABPs are. So ABP is short for algebraic branching programs. So what is an algebraic branching program? So it is a layered graph. Okay, it's a layered directed graph where so for this talk, you can assume all the edges are between consecutive layers. Okay, and yeah, so how does it compute anything? So basically the edge labels are going to be some linear polynomials in the underlying variables. Okay, and So all the edges are labeled with such linear polynomials. Yeah. So each path is set to compute the product of the edge labels that are on the path. Right? And the ABP altogether is supposed to compute the sum of all the ST paths, like S to T paths. Right? There is a sort of matrix multiplication way of looking at it, but yeah, this works. So this is an algebraic branching program, similar to a Boolean branching program that maybe some of you have already seen. Right? So this is, yeah. Okay, and yeah, so one parameter of interest, which is the size of the ABP, is just going to be the total number of vertices that appear in this entire graph. So you sum up all the number of vertices in each of the layers. And it's 9 in this example. So, yeah, I mean, it's important if you count S and T or not. So, yeah, so what are read-once oblivious ABPs? So now what will happen is, okay, so we are going to make the edge labels, like we are going to change them slightly. It's a different kind of simple polynomials, right? So instead of being linear forms on all the variables, they're going to be univariate polynomials. Okay. And further, if you look at each layer, so each layer will have univariate polynomials in one designated variable, right? One specific variable. And in fact, designated in the sense each variable uniquely appears in exactly one layer of edges, right? So so this is why it's called read-once oblivious, because each variable is read exactly once on any ST path. And while you're reading that variable, you don't get to see any other variable. So it's oblivious of the other variables. You're reading each variable exactly once. So an n-variant degree D width W ROABP will have n layers of edges. So n plus 1 layers of vertices. The univariates that are appearing are going to be of degree at most D. And width is just the width is just the maximum number of vertices in any layer. So yeah, so given an ROABP, it computes a polynomial, or you can look at it the other way and say that this polynomial has an ROABP of this width. Okay, so that's what an ROABP is. Yeah. So okay, one more thing that is, so I just told you that each variable appears once, and here I have sorted them in the correct order. But you're allowed to, and ROABP is allowed to read the variables in any order. So this is an additional parameter about the ROABP. So firstly, notice that width is sort of determining the size, because there are going to be exactly n layers of, like n minus 1 layers of vertices in the middle. So the only parameter that sort of dictates the size is the width. Right? So which is why instead of size, we are now looking at width. And so order is the other parameter about the ROABP. So it's just the permutation on the vertices that is given by the order in which you are reading the variable. Right? So yeah, so for ROABP, there is n, d, w, and a sigma, which is a permutation. Okay, this is okay. So now I'll tell you what is known about ROABPs. So as you can see, it's a very simple model. And so okay, so firstly, this order, you might ask why are we being so particular about like which order it is, because it matters. So you can look at this polynomial, which is just the product of xi plus yi over all I from 1 through n. So it has 2 n variables. So if you do it in the correct order, which is why if you read each xy pair, right, together in any permutation, but it's together, each xy pair, read them together, xi, yi, then it has a width 2 ROABP. This you can probably just. But it is known and it can be shown that this requires width 2 to the n whenever you decide to read all the x variables before all the y variables, or the other way around. Right? So of course, so it's extremely sensitive to the ordering, the width of the ROABP that your polynomial will have. So this example is clear. Okay. So now what is known for ROABPs? So it turns out that the width of an ROABP for any polynomial can be computed exactly. Once you tell me what the polynomial is, in the sense you can tell me what the coefficients are and so on. There is a way which I'll get to later. You can compute exactly what the optimal width is. I mean, what the width of an ROABP, width of an optimal ROABP for your polynomial is in each layer. You can tell how many vertices are in each layer exactly, no constants, nothing. Right, so this makes lower bounds easy and therefore not interesting. So what people look at is the harder question of identity testing, which you earlier saw. So yeah, so when the black box version of it, which I told you about, there we know quasi-polynomial time algorithms. Basically, the exponent is logarithmic in the number of variables. Yeah, this is the general thing. There are polytime algorithms in some specific settings and so on. But but if I allow you to see the ROABP, then in fact there is a polytime PID algorithm, right? Which is different from what we were doing. So now instead of querying, you can do more things. You can. Right, so this is the identity testing, and as I told you earlier, once your identity testing things show some promise, you can ask the harder question about reconstruction. So yeah, so without going into too much detail of this, so what is known for reconstruction of ROABP, especially the proper learning part of it, is that if I tell you what the order is, so remember, like I'm giving you a black box and I'm giving you some basic parameters. Like for ROABP, it will be N, D, and W. If I also tell you what the sigma is, then you can reconstruct the ROABP even in worst case. Right? You don't need any non-degeneracy guarantees on your input. I can just make some queries and construct the entire ROABP. And in fact, I think I'll get the optimal ROABP, which is coming to Varun's. Sorry?
What was D?
D is the degree. So you can think of it as the degree of the polynomial or the individual degree. It's the degree parameter in the ROABP. Like each edge label is a univariate of degree D.
And sigma is the order.
Sigma is the order. Yeah. Yeah. So throughout it will be N, D, W, and sigma will have those means.
So isn't the case that for every sigma you get a different circuit? Like what is the over some sigma you don't have a circuit,
So yeah, so one of the main issues is that
like when you say you're given the sigma, what does that mean?
no. So basically, I mean the order of the circuit sitting inside the black box. It could have multiple, like it could have almost the same ROABP in multiple orders. Yeah, but that is true. Like for each sigma, you could have a completely different looking ROABP. Yeah, that is some other thing that I'm also interested.
Not be
No, there will always be, but it might just be very large.
the example you gave.
Yeah.
It's an example of for a particular.
So it's
sigma.
exponentially large.
Yeah, it is as large as you want.
Yeah.
Like, yeah.
Because
Yeah.
you can always just add compute the polynomial one monomial at a time.
Yeah.
So,
Yeah, a monomial is a trivial, like width one ROABP, and it is closed under sums. So, yeah, sorry. So, and every polynomial has an ROABP of width at most b to the n. No. This is known. This is like so. For instance, there's Read-once Oblivious and NISER work, and there's many other. Yeah, but this is all when the order is given. So like, the only question, which is the sort of the question of the whole talk, is what is the complexity of finding the order? I give you a black box that has an ROABP inside. How much time do you need? How many queries do you need to figure out what is the correct order in which?
Also, like, why can't you get rid of it? Another question seems like obvious one is to get rid of to have order one in the exponent, right?
For
We don't know how to do that even for.
even PIT we don't know how to do that. Yeah.
Oh, I see.
Even in black box PIT we don't know. So okay, so that's the. But yeah, I mean I'll come back to that later. Yeah, so so let me say it again. So it's almost like if you get a black box PID algorithm, then all of essentially the same complexity you get a reconstruction algorithm, which is like in the no order setting.
No, but I should say that, I mean, like, the fact that we don't know black box PIT shouldn't rule that out, right? Because here we are okay working with the randomized algorithm.
Yes, that's
So-
also true. Yeah.
I mean.
No, but so I think
Randomized
is looking at determinant.
Oh, sorry, sir.
Randomized is just
Oh,
polynomial. Yeah.
Yeah.
But the randomized polytime is also when the algorithm is given the order.
Yes.
So the randomized polytime is still unknown if the order is not.
Yeah.
Yeah.
If you do randomized polytime, you'll see that you'll be very famous.
So here when you say complexity of finding the order.
It's not the order.
Okay.
An order.
Given
So I'll define the problem properly.
Okay.
So
Sorry, but
so-
did you say that if you were able to do the randomized polytime when given an order?
no, without giving an order.
Sorry, without giving an order, that would.
That would put NP inside BPP.
Oh.
That's the result.
Good thing.
Yeah. Yeah, okay. So what is the order finding problem now? The technical. So given parameters NDW and a polynomial F, like given as a black box, or so I'll not tell you how it is given currently. So think of it as black box for now, but we'll get to. You have to just find some order in which some order sigma in which F has an ROABP of width at most W. Right. So any order is fine. So it can have multiple, and one of them is given.
If there exists one.
Yeah, exactly. So that's what I'm getting to.
Oh.
So the point is, if I tell you a W, you can, I mean, if I give you an order. So, okay, so suppose you have an algorithm that solves that first question in this promise setting where you're promised that it has a W with ROABP. You can run that algorithm, get some sigma. If the sigma is incorrect, you can always run the reconstruction and figure out if the sigma is incorrect. You do reconstruction, you have randomized access, right? So you can do PIT and figure out if it actually outputted the correct order or not. I mean, a correct order should make this change. Yeah. So, which is why you can assume that the promise is there. Because you can do binary search over 1 to t to the n and all sorts of things. But yeah. And this makes so you can think of the following decision problem, which is you have to just which is only simpler, right? So I give you n and t and a polynomial that's n variables, degree t, right? And a parameter w, and I ask you if f has an ROABP of width w in some order. Just a yes/no question. This is the decision version of the order finding or the ROABP width problem in general. Right? So this is what is the decision version problem. Other things. So the question is clear. Then okay. So yes, this is what we show. We show that this is NP hard. So the order finding problem defined in the previous slide is NP hard, even when f is given as an algebraic circuit. Right? Not even as a black box. I'll tell you what the coefficients of them. I mean, I'll give you a circuit computing f.
I'm confused. So this regarding about ROABPs, right?
Yes,
So
yes.
what do you mean when f is given as an algebraic circuit?
So okay, so think of the proper reconstruction thing, right? And so I mean, the original reconstruction problem. I provide you f as a black box. Right here, it is only stronger. I'm giving you f. You can see f, but of course, if I give you the ROABP, then reconstruction is trivial. Yeah,
you're right. That is, you see as a white box the circuit.
Yeah, but circuit in a different model. If I just give you the ROABP, then the problem is trivial. Yeah. So yeah, so this is the other thing you can ask, and so we'll see that this is going to be a sum of monomials. Even in that setting, it is even for sparse polynomials. Right. And in fact, turns out you also get some sort of so this kind of problems are called circuit minimization, because I give you a circuit in one model and I ask you a weaker model if it has a representation in that model. So these sort of fall in the circuit minimization problem. There is also an MCSP variant of it, which is so basically I'll give you the polynomial as a truth table or the coefficient vector, what is called the dense representation. So I'll just give there will be an ordering on the monomials fixed beforehand, and I'll give you the coefficients in that order, thus telling you what the polynomial is. So yeah, so basically it turns out this problem is hard even for constant degree polynomials, the polynomials that have constant total degree. And even for such polynomials, it is NP hard to find the order. And once you have constant degree, the dense representation does not have long size, it has poly n size, which is why this works. So it turns out it is NP hard there. Yeah. So the only other result known of this kind is Costa's result about tensor rank, where you give me the tensor and you ask me what is the rank, and it's NP hard to tell apart between it having some rank or one more. And there is also warning rank, but it is closely tied to tensor. So that's the thing. So okay, so NP hard, but then what do you do? So you basically ask them for average case algorithm. You say that, okay, there are some instances which are very hard, but what about an average instance, or what about a generic instance? So it turns out generic instances you can solve in sort of polynomial. This is going to be quasi-polynomial for some settings of parameters, but for the usually interesting settings of parameters, this is.
Sorry, one thing that was not clear is that the order finding for the decision version, when you say it is, it's NP hard.
Yeah. So I'm calling it order finding because I wanted to use the same word throughout, but you can think of it as a width problem. I ask you if it has an ROABP of that width.
So is something known for some gap sort of questions? Like in the sense that I guess here it's like you're asking is there a width WABP or not?
Mhm.
But is it interesting to sort of say, I want to know if it is less than width W or requires width more than, I don't know, W bar 10?
Property testing.
Yeah, and I don't care
Yeah,
about the.
so under what is called the small set expansion hypothesis, it cannot be approximated even to a constant factor.
Oh, I see.
But so I'll get to that. So we
Okay.
do, I mean, so that just happens because our
Because of
reduction
the reduction
is very clean, and that problem is hard to approximate. So this also becomes hard to approximate.
Okay.
Yeah, we also know that, or I'll say about it at least. So these are the results. NP hardness, I mean, these are some of the results. So NP hardness for some cases of order finding, and an average case algorithm, a randomized average. If you're doing average case, like what is randomness? Yeah, so yeah, so these are the results. Okay, so I'll tell you, so the proofs are not very technical. So I'll tell you, try to give you the idea of how we are doing this thing. Yeah. Okay, so let me do that.
Sorry, just intuitively,
Uh-huh.
these two results, I just want to really understand where random or generic is relevant. For instance, one of the things that will happen is that if we generate a random read-once ABP in a particular order,
Mhm.
and we switch the order of any two, like we split any two variables,
Mhm.
and look at the resulting permutation, the partial derivative matrix will have necessarily larger rank.
Yes, that's basically what happens. So essentially,
That's like a
if
witness.
if you generate a generic ROABP in some order, yeah, I mean, I'll tell you. But so basically, it doesn't have like a search. You can search for the order without getting confused too much. Your algorithm will be able to navigate.
Sort of keep moving towards the right order and something, or what are you?
No, I'll tell you. Yeah. So I mean that might be another algorithm. The algorithm we have does not do that, but.
Oh, sorry, just wanted to know whatever you said, you said, if you take a random ROABP in a given order,
Mhm.
then flipping any two
So basically,
variables in the order should blow up the RAM.
Yeah, exactly.
It's unsaid.
So for any other permutation that is far enough from it, I'll get to what far enough is. You don't expect an ROABP of width W. The bound should only be the trivial bound that you get starting from the first ROABP that you generated. So we'll get. Okay, so
What is the average case algorithm to randomize the polynomial for? Well, you're still given. I mean,
it's a randomized algorithm which worst case runs in exponential time, like e time to the n, to the order n. But on a generic algorithm, it will on a generic input, it will halt in poly time and output a correct order. Polynomial cause.
Generic is on what field?
Yeah, so basically any large enough domain, I mean, so basically, so we'll have some parameters that we are sampling IID. So whenever the distribution is nice enough to support Schwarzschild, it just works. So yeah, so normal and everything is fine, but any large enough field is. Yeah, so we'll get to. Okay, so so I'll tell you first about the hardness result. Okay, so So what do we want to do, right? We want to find the order.
I still get confused on the last. I mean, if you're given a generic ROABP,
Yes.
so then I mean, this is a order finding is this decision version, right?
But order finding is a search problem. I mean,
Uh-huh.
like this, when he's writing the last one, I think he means a search problem.
Yeah, I probably should have used different words. So yeah, so that problem is more like ROABP width, and this is the order finding. Yeah, okay. I mean, okay, just to spend 1 minute. So because if you, I mean, the decision version, if you say, does the polynomial have an ROABP in this order, then that we know.
Right.
Like if you tell me the order, I'll try to reconstruct. Whenever I fail, I'll say no, it doesn't.
Yeah.
So that is an easy problem. So the sort of width thing is what we. Yeah, okay. So let's get to the hardest part. So what do we want to do, right? We want to, so the way I think of it usually is that you want to hide the permutation, right? So your ROABP has some order. I mean, you want to get a reduction from some NP complete problem. Okay. So what you want to do is you want to generate a polynomial for which it is hard to find out what the order is. Right? So you want an NP-complete problem where the witness is something, and you want to say here the witness is order. So you want to sort of set up a reduction such that if you find the order of your find an order of your ROABP, then you will get the witness for the NP problem. So it's what are the good, like what is the candidate NP problem? So turns out there is this nice problem called class of problems called arrangement problems, linear arrangement problems on graphs. So what are these problems? So suppose you have this graph with a 5-vertex simple graph, right? So a linear arrangement of this graph G is you basically pick some order on the vertices of the graph, right? And you just draw all the edges. Okay. So now you can ask for multiple ways in which you want the correct order or the best order. For, what is the best linear arrangement? You need some parameter, best with respect to what? What am I trying to minimize? So the thing that we will use is what is called the cut width problem, or sometimes also called the minimum cut linear arrangement problem. Right. So what is the cut width problem? So you are just saying that the cut width of a graph is the minimum over all orders, minimum over all arrangements of the cut width with respect to that arrangement. And for a fixed arrangement, the cut width is basically you look at all the cuts, like vertex I and ith and I plus 1th vertex, and see how many edges are crossing that. So for this, the cut width is 3, and I think it's optimal because the cycle with chord, right? So it's a cycle with chord, so you can, no matter how you arrange it, it will always have one place where there are 3 edges crossing. So yeah, but this is the problem. This is called the cut width problem. So given a graph, you are supposed to find out what is the optimal order, or you can ask for a decision problem. Does it have a linear arrangement in which the cut width is smaller than some parameter? Right? Is the problem clear? Okay. So yeah, you can probably already see the similarities, right? But let me just make it very explicit. So this is the formulation of cut width: minimum over all arrangements, maximum over all cuts. Right? This is the same as ROABP width. So if I give you a polynomial f and ask you what is the ROABP width, the optimal ROABP width for f, it is exactly the minimum over all orderings of the variables. And once you fix the ordering, it's the maximum number of vertices in any layer. Right? So it already has this written out for you. You just do pattern matching, and what you want to do now is you want to say the number of edges crossing the cut should correspond to the number of vertices in a particular layer. Right? And that is exactly what we're going to do, thanks to this. So this is a theorem that I told you earlier that given an order, given the polynomial, I can tell you exactly how many vertices you need in each layer. This is that theorem. This is implied by a work of Nissan, whose work was on some other kinds of ABPs, but it works for ROABPs as it is. So basically for any polynomial f, the optimal ROABP for f in an order sigma will have exactly these many vertices. So there is some matrix that you draw with respect to f and sigma and I, right? I'll define the matrix, but the rank of that matrix is exactly the number of vertices, right? No other factors, it's exactly the rank. So this is, if you're, I think, but correct me if I'm wrong, but this is sort of the, so this matrix is motivated from the communication matrix thing, and so you don't need to conjecture it is true here. The rank conjecture is true, but so that's the, So what is this matrix? So this matrix is exactly following. So what you want to do, you want to look at your polynomial and ask for, so think of an ROABP as, so you read some variables, right? And they are not going to appear again. So you have to remember some information about the variables that you have read. So the number of vertices you can think of as a measure of how much you want to remember. Okay. Turns out this measure is exactly the rank of some matrix. So what is this matrix? You just want to, so I told you it's already like communication matrix. So you want to know the width in the ith layer. So you have read I variables, right? So think of these as the Alice variables. These are the Bob variables. So the rows are going to index now monomials, because in the algebraic part. So monomials over the first I variables according to sigma, and the columns are monomials in the the other n minus I variables according to sigma. Right, so the left and right variables. And you're asking for how much do I need to remember? It's exactly the, okay, so what are the entries? The m comma m prime as entry is the coefficient of m times m in your final polynomial. So to draw a parallel with communication matrices, you had evaluations like these settings to the left variables, settings to the right variables, and this was like what is the value of f at the combined point. Right? But here it is the coefficient matrix. Right? So this the rank of this matrix, and in fact the rank of these n minus 1 matrices for all the n minus 1 cuts, they exactly tell you what they are. Right? And in fact, all the reconstruction and everything, this is the crucial component. And like just to give one more line, it's just so the point is testing rank of this reduces to PID, which is why you, if you have randomized thing, you can just basically, as whenever you get PID, you get reconstruction. Yeah, so this is the matrix. So we are going to use this characterization. I mean, I won't tell you exactly the final details of it. But yeah, so what we do with this characterization in this particular cut width problem. So we do the following. So this is a lemma that we took. I mean, this is the sort of the core of the reduction. And so given a graph G on a set of vertices V and set of edges E, so it's a simple undirected graph, undirected, unvectored. Right? So we can compute a polynomial Fg in polytime in the size parameter. Such that firstly, I mean, the number of variables is going to be the number of vertices in the graph. Right? And for any order sigma and for any I, right? If you look at the number of edges crossing the IF cut, like the first I vertices and n minus I vertices, that cut, the number of edges is going to be exactly the rank of the IF matrix that we drew earlier, minus 2. I mean, or rather, the rank is exactly equal to the number of edges crossing the cut plus 2. This plus 2 is unavoidable because of some corner cases you need to handle. But this is what we, so it's as clean as this. So I had shown you this pattern matching thing earlier. It's exactly that. You just replace, and the number of vertices is exactly the rank. So you just put rank there, and there's some plus 2 here and there. So okay. And furthermore, this polynomial is simple in more than one way. So the degree of the polynomial, which is the total degree now, is at most twice the degree of the graph. Right. And the individual degree of the polynomial is exactly, you can bring it down all the way to degree of the graph plus 1. So, yeah. So if you give me a constant degree graph, I'll give you a constant total degree polynomial. Yeah, so if you give me a 4 regular graph, I'll give you a multi-atic polynomial. Right? And the individual degree will be like 5. And it's sparse. Right? So for each edge, I will add exactly one monomial, and there are some other monomials to make sure that corner cases are handled. It's a sparse polynomial. The number of monomials in Fg is m plus n plus 1, where m is the number of edges, n is the number of vertices. Right? So it has at most n squared monomials, like order n squared. Yeah. So yeah, so now there is this result by Monian and Sudpur. I hope I pronounced the names correctly. So it says that cut. So firstly, cut width is NP complete. So this is known from before. This is the reference for this is the Gary Johnson list of all the right. But they show that it is NP complete even for planar graphs of degree 3. Right. So basically, you put this right there, and then you get that for degree 6 onwards, we get NP hardness. I mean NP completeness, NP hardness.
Because this degree is constant, you have the dense representation.
Yes. Yeah, so that's the, yeah, so this is the algebraic MCSP thing comes from here. This 6 is basically 2 times 3. So from 6, it's, yeah, so from degree 6 polynomial, so this is going to be some into the 6 size vector of coefficients. So I'll give you that, and still, so this will give you the graph in some sense, right? But still, even if you know the graph, what will you do? You can't find out cut width unless p is equal to n. Okay. Yeah. So what happens in the other thing. So the thing is, once the degree starts growing, the truth table length sort of explodes. It could be like exponential, even if your degree is like n over 2 or something, but any constant times 10. So in that case, but remember that still we get a sparse polynomial. Polynomial only has n squared coefficients. So it has trivially has circuit, depth 2 circuit, sum of monomials, representation has size about 1, n cubed. Right. So this is the, I'll give you white box, I'll give you the circuit, like this is the polynomial exactly. So this is sometimes called the sparse representation. So dense representation when degree is constant, sparse representation still remains NP. Right. So yeah, so the bad news, the summary of everything is that worst case, we can't learn ROABPs. Okay, so
Does this show something it feels like what it shows is that you give me a polynomial in let's say normal places and some parameter W. What's hard is whether there is a read-once ABP with W in any order.
yes, yes.
That's what
Yeah, that's what it says. So basically, if you like, so think of the proper learning kind of the reconstruction setting in the beginning. So if it's
and the question of so promise question where you give me a polynomial which has a read-once ABP of with W in some order sigma. Finding that sigma somehow reduces to this.
yes. Again, it's the same. Yeah.
So the cut width hardness question. So it basically says that it is hard even when the degree of the graph is very small. Right?
Yes.
Which one way to phrase that is by saying that you give me an instance of cut width computation of a large degree graph. I will tell you how to reduce that question to a cut width computation of a low degree.
Yeah, I don't know if that is exactly how they reduce it, but yeah.
I mean, that must follow because it is NP cut, right? I mean, because that is NP, so there must be a reduction.
Yes.
I was wondering, does that translate to ROABP width? Like in the sense that suppose, is there a, I don't know how to phrase the problem correctly, in the sense that I have a polynomial which has small width in some hidden order, but not in another order or something. But maybe my current polynomial has too large a degree.
I see.
And is there a generic way in which I can take such a thing and somehow do
The start polynomial.
Yeah, somehow make the, in some sense, retain all the important things about the polynomial, but somehow reduce the degree.
So we have not looked at it. So basically, you are saying, can this result be proven directly from this instead of using cut width? Yeah, we have not looked at it. But yeah,
but there's something slightly weird about it, right? Because in the constant degree regime, the PIT question is easy.
yes. Yeah.
So
So such a reduction.
yeah, it's somehow such a reduction would be.
No, but maybe the width would blow up or something a bit. Maybe it becomes quasi-polynomial or something.
Okay.
Yeah. Because the degree, the total degree is reducing. So it's a, if it was just individual degree, there are some basic syntactic things that we can do, but I don't know total degree how to. Yeah, but it's a good question. I have not thought about it. Okay, so this is how we do the hardness results. Yeah, so now so I'll give you the worst case. I mean, basically it's the same algorithm. Worst case, it runs in exponential time. I mean, in fact, e time to be specific, 2 to the order n. And average case, it will run in poly time, quasi-poly time, depending on the parameters. So firstly, e time is non-trivial, which is why I want to say this algorithm. Because what is the naive thing to do? Naive thing is to just go over all the orders one by one and run the known order reconstruction. Right? And yeah, so that would be one. But yeah, how do you beat that? So that's the first thing, right? How do you beat n factorial or n factorial times poly n? Right? So recall that NISER's characterization says the following. So the ROABP width of F under an order sigma is at most W. If and only if all these cut ranks that you had, right? We wrote n-1 different matrices for different cuts. If all of them have rank less than W, less than or equal to W, right? Then it has an ROABP of that width. I mean, and vice versa. Right characterization. So for instance, take an example of n equal to 5 and our old permutation 5, 2, 3, 1, 4. Then all these ranks have to be small. The rank of when you draw the matrix, with 5 being the left variable and the rest being the right variables, then 5, 2, 5, 2, 3, and 5, 2, 3, 1. So all the, oh, sorry. Yeah, sorry. Yeah, so all these ranks have to be small, right? And yeah, so just for if you have forgotten, so when I put a set up there, I just mean that that set is the left side of variables, the complement is the right side variable. Okay, yeah, so let's try to visualize these sets, right? So let's draw them like this. So these sets have to have, so for all these S, M, S, F has to have small rank. Right, and there is a reason I've drawn them like this is I want you to imagine them as inside a hypercube. Right. So these are growing sets and they form a path, and in fact these are trivially there. All the variables on one side, right or left, of course the rank is small, the rank is 1, just a vector. Right. So basically what I want to tell you is that whenever F has an ROABP of width W in some order sigma, right, you could draw a subset of the Boolean hypercube over n many variables, and a subgraph of the Boolean hypercube. And what I mean subgraph here is that it's the Hasse diagram thing. Like there is an edge only when you add only one element. There is an edge only between like consecutive layers, right? Otherwise, it's the inclusion. So there is some subgraph you can draw. So what is the subgraph? It's just the induced subgraph of the Boolean hypercube, where a vertex is included if and only if the rank corresponding to whether vertex, which is a set of vertices here, a subset is included if and only if the rank corresponding to that subset is small. So you start with all the 2 to the n subsets, you delete everything that don't have small rank, and you get some graph. Let's call that edge sub W of F, right? And any sigma which gives you an ROABP actually is a path in this graph from the empty set to the full set, right? So this tells you now what the E-time algorithm is. You just compute this guy. So okay, so firstly this, I think I'm going to say it again. Yeah, so this is F has an ROABP in order sigma if and only if there is a path dictated by sigma in the hypercube, like the subgraph. So, and it's a fact that you like checking. So if I give you a subset S and you know the polynomial, you have a black box computing the polynomial F, then checking whether this rank is less than W, it just reduces to a single PIT call. Okay, and so slight technicalities. This is general PIT, not ROABP PIT, but like if you know the order, then there are some certainties here, but it reduces to general PIT, but like still the efficient Schwarzschild case. Okay. So this makes this following algorithm. So first you can do as the first step, you can just populate the graph, right? So the exponential time algorithm just goes over all subsets and figures out which vertices should be there in my subgraph. This gives you the graph H sub W, and then you just find a path in it. Right. In fact, let's be a bit more greedy and let's say I don't want the entire graph H, right? I just want something that gives me a path. So let's just greedily do a DFS from the empty set and just try to reach the last layer somehow. So that will be a thing, and worst case it can make you go over all subsets. So just 2 to the n time.
No, but every such path
Yeah.
did not compute the same the polynomial in question, right?
No, it does.
It does.
Yeah. So basically,
Oh, yeah, because you're looking at the same matrix.
Yeah, it's the same polynomial.
Yeah.
Yeah. So you just then find the path in that graph. Okay. So this is the exponential time algorithm. Exponential in the worst case. Yeah, I'm saying E because exponential 2 n factor is also exponential, but this is better. Yeah.
Exponential is 2 to the order n.
2 to the order n time.
E versus X.
Yeah. There are some poly in D and W factors. If W is large, it will start dominating, but yeah, they are coming from PIT.
No, but where then are you using the PI because of the rank?
To rank, yeah, to compute to find out whether the vertex should be there. Okay, so yeah, so very little remaining. So let me go over that. So how do you make this up? So why does this run in efficient time or generic in the generic setting? Is okay. So what is generic? First of all, I had sort of said it earlier informally, but think of this as So let n be 5, d is whatever your favorite number is, 2 is the width, right? So what you will get, so you just compute the complete graph of the ROABP of width 2 in some order sigma that you want to fix, right? Now what remains to, so if you want to, like what remains to fix in this ROABP is the labels of the edges. They are some univariates of degree d, so there are d+1 coefficients. Sample all of them independently, identically. Right? That is what I mean by generic ROABP. So any polynomial that is like you do this and then you let it run, compute a polynomial. That polynomial has an ROABP of width 2 in the order sigma just by definition. So this is a generic ROABP. So this is the distribution over the polynomials that we are talking about. Okay, so yeah, in general, you have these bunch of parameters, and generic ROABP for those parameters is exactly what I told you. So just for some thing, there are some n d times w squared. So there are w squared polynomials in each of the layer, right? W squared edges. Each of them will give you some d+1 coefficients, and there are n-1 layers. So this is the, so there are n layers of edges. So yeah, so this is the roughly the number of things that you're sampling. And some distribution d, which is nice, which lets you do Schwarzschild. Okay, so this is the definition of generic ROABP. Yeah, so now what is happening, right? So we want to know what are the bad inputs for populate graph. When does this populate graph thing, which was just computing a subgraph of H, starting a DFS, like, yeah, what are the bad inputs for it, right? What should happen? So what we want to show is that these bad inputs are special, right? So a generic input will not be bad with high probability is what we want to show. But sort of the algebraic geometric way of saying it would be slightly different. We'll say that all the like inputs that make your populate graph run for a long time, they sort of form a smaller dimensional variety. If you don't know what it means, it's fine. It just means like you can think of it geometrically that they all sit in one corner. So
You have to satisfy the equation.
Yes, yes.
Equation is important.
Yeah, equation. Yeah.
That's all.
Yeah. Yeah.
And small, yeah.
Yeah. So what is a bad input? A bad input is an f for which this graph h sub w of f has a lot of vertices, right? And somehow basically, so we are doing a DFS, right? So basically your DFS goes on many wrong paths and has to backtrack from it because it can't extend those paths in like, it tries to, so suppose it reads like n/2 minus 1 variables. Now it looks at all the n/2 plus 1 candidates for extending this and it cannot extend. So it has to backtrack. Right. So imagine it doing it for almost every.
But you can't do the populate graph right at the beginning, right? Because that will already take 2 million time.
Yeah, I mean,
So
currently.
you will do it,
No, we do it, and so somehow in generic case it still gives us. Like, I mean, it's yeah, I know it's not a very clever algorithm, but it still works. Like, so I don't know.
No, I'm just saying that. Sorry, what are you aiming for now?
So I want to show that for the generic input, this won't run for too long.
Yes.
Populate graph itself will not run
No,
for
but
too long.
populate graph, I mean, you probably will modify that.
Yeah.
Because previously populate graph was like, for every subset you were.
Yeah. So which is why, yeah. So I said that, but I mean, so then I again said that I don't want to get the whole graph. I just want a subgraph which gives me one path.
Yeah, so you will.
I'll do a DFS.
You will populate the graph.
Yes. So I'll do a DFS and I'll do a DFS until I reach the nth layer. I don't care if I explode all the words. Yeah. Sorry. I mean, yeah, that's the. Right, so basically the DFS should not have to, I mean, on a bad input, the DFS will have to backtrack from a lot of bad paths. And you don't want this to happen. In fact, what we are going to show is that on a generic input, this graph HWF only has the obvious vertices. So what are the obvious vertices? So because you generated F using this order sigma, there will be vertices corresponding to the path given by sigma. Turns out you'll also have vertices corresponding to, this is just because rank of A is equal to rank of A transpose. Right? So you also have a reverse of sigma, not the inverse. The reverse of sigma, the reverse order also has a path. Okay. So if W and D are well behaved with respect to, so if W, how do I say it? So if W is at most poly D, then these are exactly all the vertices in HWF for a generic polynomial. Right? if W is slightly larger, let's say D is a constant, right? You're looking at multilinear polynomials or something. Then basically there are cases when this matrix has small rank just because it has very few rows or very few columns. So those guys also show up. So the only obvious vertices are there. So obvious is in two ways. One is either because it is a prefix or a suffix of sigma, or because just that it is so small that the MSF is very skewed, and which is why it has small rank. So yeah, so essentially we show that. So for any inconsistent S, which means any non-obvious S, the property, I mean, so if you sample, you look at the space of all ROABPs that are generated using the generic thing, right? Then those of them that also satisfy this rank being small, for any inconsistent S, they have to satisfy an equation that is independent. So yeah, so which means they form a subvariety of a smaller dimension. It's a strict subvariety. Yeah, and yeah, so this you can then do, like you can make it probabilistic by just using Schwarzschild. So, right. So the probability that you will sample a point that satisfies an equation is like 1 over total degree and so on, similar to Schwarzschild. So there is an algebraic geometric thing about varieties and all, but you can use Schwarzschild and make it like probabilistic. So that's the whole thing. And so the domain has to be large enough, or basically the distribution has to be nice enough to support this. It should not be that your field is size 2 or something and you are not looking at a multilinear polynomial. Stuff like this. Yeah. So that's the whole thing. Yeah, so any questions? So basically, yeah, so this log DW is coming up because, so this is the size bound, so above which S will not trivially have a small rank. Because so n to the, so this is exactly the number of, so if the size of S is this, then this is the sort of the number of rows or columns that you, no, not that. So D to the this will be W. Yeah. So those many subsets have size that much. So that's it. Okay, so yeah, so this gives you average case algorithm. Basically, the algorithm runs in time n to the order log DW, as I said earlier. So this, okay, so I'll come back to, I'll come to this domain being large enough. That large enough is 2 to the n. I've written 10, but it should work for 3 or 4 or something. Right, so this is polynomial time whenever D is poly W or W is poly. Right, and quasi polynomial even when D is just constant. Right, so why does this 2 to the n show up is because yeah, so what we end up showing is for like the guarantee that you get is only for a specific subset, specific inconsistent subset. And you then want to show that none of the inconsistent subsets are going to have small rank. So you want to do a union bound over all of these ones. And there are other reasons why I don't know how to get past this union bound currently. I'll get to them later, but yeah, offline I can talk to you. Yeah, but this is why this 2 to the n is showing up. So it is possible that it can be made small. Yeah. So yeah, so what did we do? So yeah, just to recap, ROABPs is that model that I have seen so many times now. So they can be properly learned efficiently, randomized polynomial, when the order is known. Right, and this is in the worst case. But finding the order, if I don't tell you what the order is, turns out to be NP hard. So worst case, this problem is NP hard. You can't properly learn ROABPs. Right, and as I told you, this is sort of the only other algebraic MCSP result known apart from Ostad's work and Shitov's work that sort of follows up on. Yeah, so even in the white box setting, so white boxes, I'll give you a circuit of a different model. Yeah, but yeah, the sort of the silver lining is that you can still do this in average case, but that we know for many other models. So in the average case, you can solve order finding, which means you can properly learn ROABPs and so on. And it's polynomial or quasi-polynomial depending on the parameters. Yeah, so we also have some approximation algorithms. So remember that the cut width reduction is very clean. If your graph has cut width W, then the ROABP will have width W plus 2. So if you tell me that cut width is hard to approximate, which is the case under SSE, yeah, I mean, I know what it is, but don't want to get into a completely different thing, right? So, and that is sort of this gap kind of thing. So cut width also the gap version. But unconditionally, apart from SSE, so we don't know how to show that ROABP width is hard to approximate up to any constant or up to some constant without using this SSE currently. But the point is, if you can give me any constant approximation, then we know how to get, any arbitrary constant. So you get a p-tas. So it will run in time. So you ask me for epsilon approximation, it will run in time into the order 1 over epsilon. That's the. Yeah. So yeah, so some open questions. I mean, of course, for the average case algorithm. So can we get polynomial time for constant individual degree? Maybe a different approach, like you slowly approach the ideal order or something. Maybe that's the thing to do. But basically, it will require a different approach. You can't do this populate graph thing because it will always have these like the obvious vertices, and they will become quasi-polynomial whenever d is very small. And yeah, better dependence on domain set. Like how do you bypass this union bound that we are doing? It seems it's the first thing that we'll try, and because it worked, we didn't. But yeah, that is one more direction. Yeah, and the hardness of approximation thing that as I told you, can you show cut width is hard to approximate up to a constant vector without relying on the conjecture? So okay, so something about this. So this implies UGC. SSE implies UGC, and there is some specific form of UGC that also implies SSE, but it's a weaker, stronger form of UGC. Yeah, right. And or generally, can you show ROABP which is hard to approximate for some constant, like up to some constant? Because once you get one constant, you get a p-tas and you get results. But yeah, so can you show it is unconditionally hard or like hard under some other hypothesis? Unconditionally would be better. Can you show that if p is not equal to NP, then you can't approximate ROABP width up to some constant, some large enough constant? Yeah, that's it. Thanks. Yeah, so the ABP figures, if you like, then they are not mine, they are from second. But yeah. Yeah.
The problem remains hard. I mean, I didn't just catching on details of the reduction. Even for the monotone model.
Monotone ROABP.
Yeah.
Oh, that is. So yeah, so this is this weird setting where so I don't know if anybody has looked at monotone ROABPs, but so there this the Nissan thing breaks down, which is perhaps why you're asking.
Yes.
Yeah. So
then it starts like log.
Yeah. Yeah. So yeah, I can't think of anything of the top, but it's a. I'll think more about it and.
And the other thing is like the individual. So on the edges, you were labeling by dignity univariates,
Yes.
right?
Yes.
If d is equal to 1, then this should be easy or.
What should be sir?
No. I mean, does the NP hardness still reduction?
Oh yeah, good point. Yeah, I don't know how to do this. So we only know how to do this for d being 6 or larger.
You require d being 6 for the hardness.
Yeah, because the reduction is from cut width, but
Right.
I won't be surprised. I don't see any reason for why it should be easy below that. So it should be hard for multilinear as well.
Okay.
But
So for both monotone and multilinear, we don't know.
currently we don't know. But yeah. So yeah, I think monotone is, I'm not sure, but multilinear, I believe it should be true. I just think we don't know how to.
You believe it should be the hardness should go.
The hardness should go through. Monotone maybe. So yeah, this is always difficult because monotone it's a weaker model, so it sort of makes both sides weaker. So it's incomparable. Yeah.
One question I have, so right now the order finding question, or rather the width problem is, does there exist an order in which you have an ABP of width that was W?
Yes.
What about the situation where does this have a width W ABP in every order? If you want to, if that's the decision you're trying to solve.
Yeah, this should be easy. But yeah, so you just do Good point. I mean, randomized should work, but I mean, average case I can just see right now because the point is you just sample an order at random and run the non-order reconstruction.
No. I just
For an average thing, it will.
No, the different question. I mean, not the average case.
Yeah, the worst case thing.
We are given a circuit, and I just want to know, does it have an ROABP in every order?
Of which.
Of a bit term.
Yeah.
Does it have-
Yeah, I don't know how to do that. I mean, I can't.
Like, I don't see a randomized thing also.
No, so average case is there, but yeah, I mean that's.
Yeah, no, the worst case.
So randomized things, okay. So the gap thing is randomized, right? If you say that it either has in all orders or only 1/3 of the orders work. So in a sample permutation.
No, yeah, that's true.
Yeah.
No, but
yeah, the exact thing randomized, I don't see one.
So in fact, I mean, there are lower bounds because of NISER, right? So, I mean, even the simpler question is simpler if you are to prove the hardness. I mean, can you find an order in which the width is larger than that? Do you know how to find that?
So, I mean, for an ROABP, do we know that if there is some order where the width is bad, then there will be many orders where the width is bad?
my guess would be yes.
Yeah.
Because then.
So basically, I mean, I can tell you often, but I mean, so the sort of this, what it comes down to is that, so think of the hypercube thing, right? So if at one particular set your rank is large, then if you swap only one element from it, the rank can drop by only so much. Because that matrix can be gotten by rearranging this matrix. That's essentially where it is coming from. So if that rank is large, then this rank also should be
You
large.
can have instances where you take like, I don't know, n-2 or n-1 commuting matrices and pick one matrix which doesn't commute with anybody and it's totally random. The only permutations that are going to be bad are when you pick this guy up and they say,
Yeah,
true.
so this constant fraction thing is maybe too much to us.
Yeah. Yeah, it won't be constant fraction, but yeah. But there is some structure on the hypercube that we are not yet using. There is like, you can't have like local spikes or like this thing. It has to, it's sort of gracefully divided.
But then, from what you said, it should be like finding an order which is bad, should be a hard.
Yeah, I mean, so because it's the same, I mean, yeah, you also got it.
No, his question is a little different.
So mine was about is it true in every order?
Yeah.
But I mean, like if my answer was no, then it probably looks like the witness is like, I'll give you an order where it doesn't have a. Yeah.
So if I can solve your question, I can solve this.
Of course.
Yeah.
I mean, if you believe these are hard questions, my question should be easier to prove hard.
Yes. Sure.
And you can solve either question.
Maybe like lack of literature. This thing will work for non-commutative ABPs. Because
Non-commutative ABPs, there is only one order. So
okay. And
I mean, so non-commutative ABPs, you want to use the ROABP thing, you set multilinearize it or you make it read once by this syntactic replacement. But then the order will always be 1 through n. Yeah. So there the order finding problem is not. So there reconstruction is there. It just happens.
Okay. More questions? Well, then let's start Anamay. Then it's still not, you're still like, let me turn that off and then say what.
You have no.
Then I would be scared of Baba will suddenly pop up here and then say something.
You have no